Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Deep beneath the waves of the Mediterranean Sea, resting among the remnants of a lost empire, lies a material so rare and so pure that it has become the most sought-after substance in modern particle physics. We aren't talking about gold, silver, or precious jewels. We are talking about lead. But not just any lead. This is ancient Roman lead, cast into ingots more than 2,000 years ago. While it might seem like a strange partnership, the fields of marine archaeology and cutting-edge astrophysics have collided in a fascinating way. This ancient metal is currently the key to unlocking the mysteries of dark matter and the fundamental nature of our universe. To understand why physicists are diving for shipwrecks, we first have to understand the ghost of the cosmos, dark matter. Scientists estimate that everything we see, stars, planets, trees, and people, makes up only about 5% of the universe. The rest is composed of dark energy and dark matter. Dark matter doesn't emit, absorb, or reflect light, making it completely invisible. We only know it exists because of its gravitational pull on galaxies. Detecting it, however, is one of the greatest challenges in science. Because dark matter particles interact so weakly with normal matter, researchers have to build incredibly sensitive detectors. These detectors are usually buried deep underground, beneath thousands of feet of rock, to shield them from the constant barrage of cosmic rays from space. But even deep underground, there is a problem: background radiation. Most materials on Earth, including the very metals used to build the detectors, contain tiny amounts of naturally occurring radioactive isotopes. For a dark matter experiment, this internal radiation is like trying to hear a whisper in the middle of a heavy metal concert. To hear the whisper of a dark matter particle, the environment must be perfectly quiet. This is where lead comes in. Lead is one of the best materials for blocking radiation due to its high density. However, there is a catch. Modern lead is itself radioactive. When lead is mined, it contains an isotope called lead-210. This isotope has a half-life of about 22 years. In the world of ultra-sensitive physics, lead-210 is a loud, disruptive noise. Even worse, the smelting process used to refine modern lead often introduces other radioactive contaminants from the air. This is why scientists turned their eyes toward the bottom of the ocean. When the Romans mined lead 2 millennia ago to create pipes, coins, and ship ballast, that lead also contained lead-210. But because 2,000 years have passed, that radioactivity has had time to decay away. 22 years is a short time in the life of a lead ingot sitting on the seafloor. Over 20 centuries, the lead-210 has gone through nearly 90 half-lives. For all intents and purposes, the radioactivity in Roman lead has completely vanished. It is thousands of times quieter than any lead we can produce today. It is, quite literally, the purest shielding material on the planet. One of the most famous sources of this low background lead comes from a shipwreck discovered off the coast of Sardinia, near the island of Maldiventure. A Roman merchant vessel, which sank between 80 and 50 BC, was found carrying over 1,000 lead ingots, each weighing about 33 kilograms. For archaeologists, this was a treasure trove of Roman trade history. For physicists at the National Institute of Nuclear Physics in Italy, it was the ultimate scientific resource. After years of negotiation, a partnership was formed. A portion of these ancient ingots was transferred to the Gran Sasso National Laboratory, located deep inside a mountain in central Italy. At Gran Sasso, the lead was used in the CUORE experiment, the cryogenic underground observatory for rare events. Scientists stripped away the outer layers of the ingots, which had been contaminated by modern sea salt and bacteria, and melted down the pristine ancient core. This lead now forms a shield around a detector designed to look for a hypothetical process called neutrino-less double beta decay. If discovered, this process would prove that neutrinos are their own antiparticles, explaining why there is more matter than antimatter in the universe. Without the Roman lead, the detector would be blinded by its own components. This intersection of history and science does come with an ethical debate. Some archaeologists argue that melting down 2,000-year-old artifacts is a loss to our cultural heritage. However, the compromise reached is a model for interdisciplinary cooperation. Only the ingots with the least historical marking are those that are severely damaged or used for physics, while the most preserved pieces are kept for museum display and historical study. In exchange, the physicists provide high-tech analysis of the lead's composition, helping archaeologists map out ancient Roman trade routes and mining techniques. It is a beautiful irony. The garbage of the ancient world has become the lens through which we view the origins of the universe. By looking back 2,000 years, we are finally gaining the clarity we need to look back to the very beginning of time itself. For more incredible facts like this, don't forget to subscribe and turn on notifications.